Okay.
I mean, don't forget with the protocol, we can just say, yeah, we'll do that. Yeah.
I've got a problem with the screen.
About stratifying due to that, unless it's a secondary analysis. Do you know what I mean? Yeah. So you would say, here's the main thing. Also, we'll do a subgroup analysis later on, Yeah. So in other words, it doesn't come into the sample size calculation. No, it didn't come into it. Well, is this a grant or just a protocol? You said it was big, didn't you? Yes. I don't. Yeah, I don't know. Because I got protocol this morning because I just had to look at that. We did have it 6 months ago as well, the early version of it. Yeah, but you don't do it right like that. And it's like 60 pages as well, so I didn't. No, and plus that's not our business, basically. Well, we're not supposed to be really familiar with everyone's protocol. That's more the questions we need. And you have to make the assumption that they know what they're doing. Yeah. But yes. Yeah, we shouldn't be criticizing them on what's the point of this study. Yeah. Oh, no. Well, yeah. I mean, I think it's important. I'm just not sure why. Well, regardless of whether it is or isn't, it's got nothing to do with this. I mean, I agree with you. Do you understand what I'm saying? I'm talking about the clinical significance of the study. Right. Yeah, really, that's up to them. Yeah. Ours is about yeah. Yes, but I guess I would like to be No, I understand that. Even if it's to explain, do you really want to do this? My feeling is with the stratification is that you would just leave it as a secondary analysis. Yeah. Well, I don't think it's the primary analysis. Oh, that's simple. In that case, it's not. Analysis is overall. Right. Oh, that's easy. Yeah, I mean, that's just a subgroup analysis, you know what I mean? Which you can do in a post-hoc type of way. You can say you're going to do it. Yeah. And then just say we're going to stratify on the median or whatever into the two groups. The other problem is you're probably going to have more in the right. We're going to have more in one than the other. Well, no. If you do it at baseline, there'll be a baseline population that they can stratify at baseline. Yes. Yeah. How are you going?
Yeah, I'm okay. I can't get this screen off here. Like, you know, this AR net Cisco screen, I'm not sure how it's gotten up and it's not disappearing.
Just try tab even. No. Oh, wait, say something happened. Show hidden icons. Maybe just try your control tab. No, it's
I don't know why though. I just need to get rid of this screen. And I don't even know how it got up.
What is it?
I don't know.
It looks like a PC thing rather than a display thing.
Yeah, I agree. 54033. What's the prefix for your Q again? I forget.
Oh, I wouldn't have a clue.
Maybe it's 33.
Yeah, I mean the mouse doesn't even recognize it. God, you can't even.
Oh, it's muted. Oh, hi, this is Casey speaking. That's me. Okay, sure.
I guess it's for the office that we're not in.
It's on. I think I've got a problem with the sound. I've had a, yeah. We had a problem with the Kodak thing coming up on the screen, but I got that off, but I'm not sure if the sound is working. How do I change the view?
The view?
Yeah, so you want them to see this?
So we can go inside the tissue culture and input it loud.
Just want to make sure that we can just check that it's okay.
Does that sound coming through okay?
Mm-hmm.
Pragmatic people out there, I mean a manuscript or a grant application, whatever, to be accepted in a high impact journal or by the NHMRC or whoever. So strong research should have two main ingredients, and we really do see this in the criteria that NHMRC puts forward, is that it should be scientifically significant. It should be important research that needs to be done. And it should be of high scientific quality. In other words, it doesn't matter how important or interesting research is. If you don't do it well, it's sort of pointless. So we need to believe the findings presented if we're talking about after the event. So for example, a manuscript. In other words, a paper provides strong quality of evidence. So as a methodologist, it really is this second issue that interests me. It's also the one, at least as a research methodologist, that I have any power over, because a lot of the research I'm involved with myself is actually led by other people. So the only real thing that I can really contribute is actually making it a strong quality of evidence piece of research. So the other thing I would point out is also to the content expert or to the expert in their area, scientific importance and novelty, or novelty I should say, should really be obvious. In other words, if you're not doing research that's important, you're basically disadvantaged from the start. Okay, so I just want to really get this point across. You probably will get sick of type 2 diabetes when listening to my talks, because that's all I ever seem to talk about. All of my examples are in this area. This is one of my areas of research. So I'm just going to give you I'm going to give you 2 example studies. These are not real research projects, but really I want to get across these 2 aspects. Importance, so scientific or clinical importance or novelty on the one hand, and the second, strength of evidence. And I want you to think about these 2 things as I describe these projects, okay? So the first study is prevalence of blood sugar control in rural type 2 diabetes outpatients, and this is a retrospective cross-sectional study. So in this study, we have a single community hospital involving 120 patients. We record, well, we don't actually record, we look at outpatient records, medical records, and note the HbA1c, the glycated hemoglobin, along with some patient demographics factors, and we get this from the medical record. So this is retrospective data, it's routinely recorded data. In our sample, approximately 1/3 of patients have controlled blood sugar. We note also from our literature review that around the world, type 2 diabetes patient blood sugar control tends to range in prevalence from about 30 to 40%. So our results in our small hospital are rather typical. Okay, so first, is this important or novel? And number 2, do you believe this? Would you, for example, believe that this is representative of rural patients in Australia? In the second study, which is quite a different type of study, still diabetes, we want to know the impact of a patient empowerment program on blood sugar control in type 2 diabetes patients. So it's still the same outcome, but now we have an intervention, a patient empowerment program, and we're going to use a cluster randomized implementation trial. So here we are going to get 25 diabetes clinics from across the country. We're going to implement this trial, a power empowerment intervention that seeks to enhance patient self-management through improving their diabetes management self-efficacy. So their confidence in their own ability to take control of their own disease. We're going to have a randomized implementation sequence for the centres using a stepped wedge design. So in other words, starting with 0 centres who have the program in place, one at a time, we're going to implement them, and we're going to look at a before and after type of comparison. Our results when we did the study demonstrated that blood sugar control went from 35%, which we saw was typical, pre-intervention, to 53% post-intervention. The difference was an increase in 18% in terms of blood sugar control, and that was highly statistically significant. And you can see the confidence intervals there range from 13.8 to 22.2%. And from this study, we recommended that all diabetes clinics nationally adopt this program for their outpatients. Again, we asked the question, is this an important or novel study? Was it really worth it? And is this strong evidence? Do you believe it? Okay, so now let's think about these 2 things, and let's, again, I'm going to concentrate on the scientific quality side there. I think it's sort of obvious from those 2 studies that the first study didn't really add anything new at all. Yes, we saw that this small little rural hospital had a typical level of blood sugar control amongst its patients. And that's about that. You'd find a study like that hard to get published. In terms of just whether it's a worthwhile study. Forget about the quality of evidence. But now let's talk about quality of evidence. The first thing we might ask is, are the results generalisable in these two studies? In the first, who knows? We only had 120 patients. And yes, it was pretty much a typical level of control, but it was a tiny little study. I don't think we can say that is the typical level of blood sugar control among rural diabetes outpatients. And we might find that these results aren't particularly reproducible. If we did it in a different rural diabetes clinic or hospital, we might find quite different results. Also, this may not have actually been a typical sample, okay? In the second study, we used 25 clinics, and those results are probably generalisable to most clinics around the country. We didn't go into detail and see how the difference varied among the different clinics themselves. You know, I only really sort of wanted to talk about it on one slide, but the results are much more likely to be generalisable and reproducible, and also much less likely to be unbiased. It was a randomised cluster trial, okay? And unless there was some sort of accidental systematic aspect to our randomisation sequence, I think we can pretty much believe that, okay? So really, the study design was the main aspect here that really lent some sort of weight to the quality of evidence. That's the point I want to make. So I guess the way I want to sort of move now, where I want to move with this, is this idea of quality evidence and the amount of control we can exert on that. Okay, the way I like to think of it, God, this is a mouthful. I am an epidemiologist. Wow, try saying that fast 3 times. So I like to think of quality of evidence issues in the same way as I think about risk factors. Some risk factors are non-modifiable. There is nothing I can do about them. And some are modifiable. So non-modifiable ones might be things like genetics, gender, ethnicity, those sorts of things, biological types of ones I was born with. And the others are modifiable, like smoking. I can give up smoking, BMI, I can eat a little bit better, I can exercise some more, I can live a better lifestyle. Dietary salt intake, that's a related type of one. So why am I bringing these things up? Because I think we can think the same way in terms of study design, okay? Some issues when it comes to study design and quality of evidence, we have power over. We can actually design our studies better, or we can analyse them more appropriately, and that's going to give us better strength of evidence. Other things are outside of our control, and they're understandable. Any reviewer who knows what they're doing, or any grant assessor who knows what they're doing, and I do underline that, would forgive us that we don't do an RCT of a study about a risk factor. You can't allocate people to risk groups. It's just not an ethical thing to do. So when we are observing the impact of risk factors, we can't do RCTs. We have to do observational studies. And to do an observational study involving risk factors is a forgivable thing because you can't randomise people to risk groups. On the other hand, if I have a sample size of 100, then you shouldn't forgive me for that, because very rarely is a sample size of 100 a strong evidence study. Okay, so I really just wanted to get across that some things we can do something about, and we are expected to, where other things are just outside of our control. Okay, so what am I really doing here today? I really do want to get this across. Okay, am I here to just inflict another painful biostatistics lecture on you? As much as I enjoy hurting people with biostatistics, the answer is no. I'm not even, well, I might mention a statistical model, but you'll see no funny little symbols today. Okay, so instead I would like to emphasise the importance of clinical epidemiology and biostatistics in the health sciences. Sorry, I just realised I'm actually looking down. I'm actually not looking at you guys with some, yeah. See, even Zoom has changed the type of person I am. So instead, I really would like to emphasise the importance of clinical epidemiology and biostatistics in the health sciences. I really would like to show you how it can help you to move from mediocre research, and really by that I mean research with a questionable quality of evidence, to producing, and by producing I mean conceiving, designing, conducting, disseminating strong clinical research. As much as we possibly can. These are these modifiable risk factors I was talking about. Okay, so the discipline of epidemiology and biostatistics are inextricably related to each other. They're really sort of just two sides of the same coin. I know the traditional word epidemiology suggests disease movement through populations, but really what it has come to mean when we're talking in health research is very much the design side of our research and how we measure outcomes and those sorts of things. And biostatistics is how we then get that data and actually analyse it to produce strong evidence research. So they both relate to the research end of the health discipline. And as such, a basis in epi and biostats is really important for both health and biomedical research. Sorry, I shouldn't put biomedical and clinical research together. They're quite different fields. I was just trying to save on words. So I'm going to give you the traditional definition of epidemiology, and then I'm going to sort of throw it away because I really do want to focus on clinical epidemiology, which has quite a different definition. So epidemiology is the study of the distribution and determinants of disease, health or injury outcomes, so health outcomes, in human populations, generally speaking, and the use of the knowledge we gain from this study to control these health problems. Okay, so that is a life, the universe, and everything definition, if ever I heard one. Clinical epidemiology, on the other hand, focuses on people, technically speaking, it just focuses on people who are already sick, so clinical populations. So we could just say, you know, hospital-based studies. And by the way, I should add, this is my preference for clinical research, they're a lot easier to collect. Anyone who's had to do community-based research and clinical research will agree with me, having your participants come to you is actually a very useful thing. It really is, to actually try and get a representative sample of the population outside of the hospital setting is really difficult. And that's when they even participate, when they agree to participate. Okay, the other thing I'd like to mention just briefly about clinical epidemiology, just something I've noticed, is it seems to be very practical and very pragmatic. In other words, clinical epidemiology very much focuses at the coal face. So for example, prognostic scoring and diagnostic test evaluation, those types of studies are really to deploy a diagnostic test, or we might deploy a new intervention. So they're sort of like the end user type of research. We want to get it into the clinic. Epidemiology, general population epidemiology, that happens too, but a lot higher proportion of general epidemiology or population epidemiology studies are about identifying risk factors. They're not necessarily right down at the intervention end. Some are, but it's a much lower prevalence there. So clinical epidemiology is very much about changing practice. Epidemiology is ultimately about changing practice. Okay, I'm sure somebody's going to disagree with me about that, but this is just an observation I've made over the years. Okay, so now I'm going to give a third definition of clinical epidemiology, because almost all clinical epidemiology books, textbooks that you might read, really do this. So in practice, clinical epidemiology is about the generic research methods, regardless of a clinical subdiscipline, we use to produce strong research, and that we will hope will eventually make its way into clinical practice or policy. Okay, so it is the practical research method side of clinical research. So all we need to do now is to produce the strong research side, which is easy, isn't it? How do we do this? So again, to reiterate, what is meant by strong research? And I know you're probably getting sick of this, but it is very important you understand it. A strong study is one that is contextually and in other words, clinically important. So there is a research question that needs addressing, and that's what we're doing. And it's very clear that it needs addressing, and we need to make it so. And second, and again, this is the part that I want to emphasize, it has high scientific quality. It is a well-conceived study with an effective study design and appropriate analysis, and all of this is then packaged into a well-written paper. So, in other words, with that second thing in mind, this high scientific quality, let's split this up. Clinical epidemiology is about the generic clinical research skills that are split into these 4 steps. The problem formulation, and that is actually a very important part to it. And of course, it's going to be the clinical scientist who is, well, basically with a biostatistician or a clinical epidemiologist, which should come up with this. So in other words, these first 2 steps, problem formulation and design, should really be done together, because we very much want research, a research question that can be practically answered, okay? But again, me as a methodologist, I'm not going to formulate a problem by myself, because I don't necessarily know what's important in your clinical discipline. It has to be the clinical scientist that does this, the expert in the clinical field. Okay, so problem formulation and design. Then we think about methods, and I shouldn't just mention biostatistics here, but it's also got to do, and I guess this has to do with design as well, it's got to do with measurement as well. So sometimes outcomes or risk factors or interventions, so on, we need to be able to measure them well. And I probably wouldn't call that biostatistics itself, even though it can be highly quantitative. If we're talking about psychosocial outcomes, these might be psychometric measures. And there's a very important part of the process to make sure that they're validated measures and so on. I guess I wouldn't call that biostatistics itself. It is statistical in nature a lot of the time, but measurement is very, very important. If our measures are not reliable and valid, then they're pointless to use, okay? So methods, which is the biostatistics, and dissemination, which is really the academic research communication skills that we need to package this all together into a very, very good paper. Okay, and again, I just want to distinguish this from the clinical sciences, nephrology, ophthalmology, and so on, which are the areas of clinical expertise. We need both of these sets of skills to write a good paper. Okay, so what I want to do is now talk about, and if you've done epidemiology, an epidemiology subject before, this may be revision for you, but like most people who have done a course in epidemiology, you know, it's in the dark, vague days, way back in their training, when they probably didn't have a very good grasp on the importance of research. So I really do want to cover these basic study designs again, because I think they'll mean much more to you now. But the main factors that govern our choice of study design are 1, the research question, 2, the target population and our ability to sample it, and correspondingly, 3, our ability to control sources of bias. Okay, so those are the main 3 things that we should really consider when we choose our study design. And I know that that's a little bit vague. I know that, and hopefully I'll clear that up for you. Fortunately for you, and in many clinical studies, especially those involving treatment, we tend to be up the stronger end of the health study designs, those with better evidence. Not all, by the way, not all, but if you're in clinical studies, that's actually a useful thing. The poor people in population-based studies, they've got some hideous problems they have to deal with. Okay, so again, I just want to point something out that may not occur to you, is that some clinical studies, especially clinical trial, tend to control sources of bias, the problems, the alternative explanations that might creep into our study. They control this through design. So in other words, a randomized control trial designs out bias. And what that allows us to do is use relatively simple statistical analysis. So for example, in a lot of standard RCTs, we can use a simple t-test because all of the problems have been taken out through our design. Where we can't do this, i.e. observational studies, we need to use more sophisticated statistical approaches. So we need to use multivariable modeling to do this. Okay, so this table you may have seen before, and I'm just talking about primary data studies here. I'm not talking about things like meta-analyses and systematic reviews, which are derived from other people's research. I'm just talking about where we have the data set and we want to do the analysis. So at the top of the tree, we have randomized controlled trials. Now you'll see they have the strongest strength of evidence, and out of these studies, the lowest potential for bias. Okay, now as we go down, we go to non-randomized trials, still a trial, but we can't randomize. Then we go to the observational studies, cohort studies, cross-sectional studies, case control studies, and ecological studies. Now just note, around here it gets a little bit vague. Some case control studies have better evidence than some cross-sectional studies. It depends on what aspect you're looking at. But I am going to go through each of these and talk about their strengths and weaknesses. And again, you've probably covered this before, but just bear in mind, when you did cover it, you may not have actually had the appreciation for clinical research that you have now. So I think it's a very useful process to go through and think about these things again. Okay, so randomized controlled trials are widely considered to be the gold standard of primary data study designs. They provide the strongest evidence. How do they do this? They do things like double blinding, sometimes triple blinding. They use randomization, and randomness is the great killer of bias. So randomization, and what they do is attempt to minimize selection and confounding bias through those sorts of mechanisms. As a true experiment, and remember, in an experiment, the researcher is sort of like God. They've got power. Okay, so as a true experiment, an RCT always involves an intervention. So we sit on high and allocate our patients to groups. So we, as the researcher, impose on patients our treatment. Okay? So that is experimental manipulation by the researcher. That's what makes it an experiment. It's often not possible in epidemiological studies to do RCTs, especially those involving the study of risk factors. And as I've already mentioned, it's highly unethical to impose a protocol of risky behaviour. I cannot ask people to take up smoking because I'm interested in studying the effect of tobacco smoking on a disease. That's clearly unethical. Okay. So then we move on to non-randomized trials. So these are still trials. They're still trials. So again, we're still allocating people to treatment groups, but for some reason, and it's almost always because we can't include a randomization process. If we did have a choice, then everyone's going to reject our paper. Again, that would be an unforgivable thing. Okay, so it's because we usually can't, and we can't include randomization. That might be because of ethics, but more often it's due to feasibility. So for example, one reason might be in a single centre, we may not actually be able to randomly allocate people in a single centre because there might be contamination between patients in the different experimental arms. So we might just consider 2 hospitals, one with the treatment, one with the usual care. Okay? Now, I should make a distinction here. This is not, I'm not talking about a randomised cluster design here. Okay? So that would be different treatments used at 2 different hospitals. We would often call this a non-equivalent group design. Noting, of course, that the patients are not randomised to hospitals. If they were randomised to hospitals, it would probably have stronger strength of evidence. So it's important to think about in your own studies, or if you're reviewing somebody else's studies, what problems this might cause and what might you do to actually try and mitigate these problems, to try and increase this strength of evidence. Important to note that all experiments, including RCTs, non-randomised trials, must be prospective, okay? They can't be retrospective, of course. And if you think about that, it's sort of almost obvious. Okay, so now let's get into our observational studies. Cohort studies, generally speaking, are considered the strongest in terms of evidence of the observational study designs, okay? So again, I just want to remind you, in contrast to experimental designs, in observational designs, the researcher has no control over group membership. We are now an outsider. We have no power, okay? We can only observe what happens, hence the name observational study. The main strength of a cohort study over the weaker observational studies is that we know that the risk factor, the exposure, in other words, precedes the outcome. In other words, we know that, for example, the smoking of somebody predates the development of the disease. And this gives us a little bit better evidence to make statements about causality. Okay, I mean, they're not perfect statements about causality, but we can say the word risk factor, which suggests causality. Okay, note that cohort studies can be retrospective. So in other words, the data already exists and are not collected for the purposes of the study. So often called a secondary analysis. And we're doing here an analysis of, well, it could be routinely collected data, okay? Not necessarily, it might have been collected for the purposes of another study, but it's still a secondary analysis. That's the weaker of the cohort studies for a very specific reason I'll talk about in a minute. And they can also be prospective. So the data were collected specifically for answering our research question. In other words, the study generates the data. Also, just note that a cohort study can involve a single collection of the endpoint, Okay, they're not necessarily longitudinal. All we do know is that the exposure precedes the outcome. It doesn't mean the outcome is necessarily collected on multiple occasions. If a cohort study is longitudinal, then yes, we are following up patients and measuring the outcome on multiple occasions. So a cohort study can be longitudinal, but it doesn't have to be longitudinal. It's more about the exposure preceding the outcome. That's what makes a cohort study a cohort study. Okay, so I just want to comment briefly on longitudinal cohort studies, mainly because I do so many of them. I do a lot of analysis, and again, as far as observational studies go, they're definitely the best type of study. So generally the strongest of all observational studies are repeated observation of the participants over time. A common problem to longitudinal studies, whether they be experimental or observational, is a loss to follow-up. Okay, so patients dropping out of our study. And loss to follow-up is especially a problem when it confounds with our effects, like our risk factors, or our outcome. In other words, loss to follow-up does not occur at random. People who are sicker, for example, might be more likely to drop out. People who are exposed to a greater extent might be more likely to drop out, and that causes problems for us. Like other cohort studies, longitudinal cohorts can be collected retrospectively or prospectively. Okay, just one thing I would like to mention here, because there are a couple of, one thing you notice as a biostatistician is these urban myths that seem to creep into the thinking of a lot of reviewers and assessors and so on. And, you know, I'm not criticizing them, but we've just got to watch our levels of dogma when it comes to biostatistics and make sure that we understand this. The fact is retrospective, I have noticed, is a dirty word. It really, really is. People assume because a study is retrospective, it is necessarily poor evidence, okay? That's not necessarily the case. And I just want to mention that because a lot of retrospective studies might make up in population coverage what they lack due to precision of measurement. So for example, retrospective studies I've been involved in have had 200,000 participants in them from across the whole country. I think the papers I've written from those studies actually have much stronger evidence than prospective cohort studies from a single centre that involve 200 or 300 patients, even though the measurements may have been taken a little bit more diligently. And that is really the main advantage of a prospective study, is we can really be much more diligent with our data collection, whether that be the measurement of the clinical variables, whether they be outcomes or predictors, and just making sure patients turn up, follow up, that sort of thing. Okay, so we do have some power in prospective studies to make our data a bit better quality, but the fact is people are not paying gajillions of dollars. The government does not give us millions and millions and millions of dollars to do very large nationwide prospective cohort studies. They just don't do it. So I just think every study should be considered on its own merit. I don't think we should throw something in the bin just because it's retrospective. And people very much just stick to their dogma here. There's sort of almost a little bit of a religious fervour type of thing that actually comes into it. And I just warn you against that. Okay, cross-sectional studies, yuck. If they can be avoided, I would do so. They're often called prevalence studies because we can get an estimate of a disease prevalence from this study. They're called cross-sectional sort of for two reasons. Cross-sectional because they often represent a cross-section of the population. But they're also called cross-sectional because they're at a single time point. And this is in contrast to the cohort studies that I just talked about. before. In other words, the potential risk factor is measured at the same time as the outcome. So in other words, we shouldn't really use the word risk factor. We can only really say that what we think is a risk factor is associated with our outcome. So we're very limited on statements about causality when it comes to cross-sectional studies. However, they have a major advantage. They're cheap and they're quick. Now, the one thing I'd point out is that a lot of cross-sectional studies I've been involved with, they've been sort of PhD projects because we've got 3 years for PhD students to collect their data. If they're considering primary data, you cannot do a 10-year cohort study with a PhD student. They just can't manage it over the life cycle of their PhD. So in some research, and I'm talking particularly in population health here, I should mention that in population health studies, a lot of the time they're cross-sectional studies if they're, for example, a PhD project or a single centre study that needs to be done in a couple of years. And we are collecting primary data, not retrospective in other words. Okay? They do rely on that representative sample of the target population. Otherwise, we couldn't get a measure of prevalence from it because it wouldn't represent the population prevalence. Okay, case control studies. We usually perform these, and we perform them much more than you might think. We perform, because we don't always call them case control studies. And I'll give you an example in a minute. Why would we do a case control study? Generally because our disease is rare. Okay, so let's consider HIV. I don't know what the current HIV prevalence is, or I should say incidence rate in Australia is, but it's pretty low. So if I wanted to get a few hundred HIV patients in my study, or people with HIV, I might actually have to go and collect several 100,000 patients just to get those few hundred patients or participants with HIV. I shouldn't say patients, participants with HIV. Okay, that's how we would have to move forward if we wanted to do a cohort study or a cross-sectional study. In contrast, in a case control study, we would locate our couple of hundred of HIV participants, enroll them in the study, and then pick a similar group of people who do not have HIV, and we would compare these two groups. So in other words, we've got to be careful here because the prevalence of HIV in our sample is artificial. It's an artifact of our study design. So for example, if I have a 1-to-1 case control mix, you can't then say that the prevalence of HIV in Australia is 50%. That would just be silly. Okay, so we can't use it as a measure of prevalence, but it's actually a very practical study design. Now, what did I mean when I said that we use them much more than we think we do? Because a lot of diagnostic test evaluation studies that we do, so you've got the disease or you don't, are actually case control studies. In other words, we choose some healthy controls, we choose some people with the studies, we might be suggesting a biomarker is a good diagnostic indicator, and then we will measure this biomarker on these few hundred people. So that's technically a case control design, but we tend not to call it that. We would just call it a diagnostic test evaluation. Okay? The one thing I would say about case control studies that are not diagnostic test evaluations is their one criticism that people make is that there can be recall bias. Now, a couple of I've come across where we are talking about skin cancer or melanoma, for example, in patients, and then we will ask people about their sun exposure. So these people might be 50, 60, 70 years old. And then we will talk about their sun protection behaviour when they were 20 years old. There's going to be recall bias there. And in some diseases, there's higher recall bias in cases. So for example, Alzheimer's or something like that. There's going to be much higher recall bias in our cases than in our controls. So we've got to be very, very careful about that. I'll also mention a variant of the case control study design, the matched case control study, that involves balancing cases and controls within strata. So for example, we might age sex stratify our cases and controls. So for example, 20-year-old females, we might have one case for controls. 21-year-old females, we might have one case for controls. 20-year-old males, one case for controls, and so on. We actually do that. These have gone out of favour in the last 10 or 20 years, I guess, because better ways for analysing data have popped up. The only time I would suggest that you'd consider a matched case control study is if you're very worried that if you just sort of do it on a random basis, you might get highly lower levels of representation in one group than the other. I guess that would be a case where you might stratify. Okay, so be careful there, but otherwise I wouldn't suggest doing a matched case control study in general. I think we've moved on a little bit by that. Our ability to model out these sorts of biases is much better than what it used to be in the old days of conditional logistic regression. Okay, so yeah, I'd just talk to the biostatisticians before you go ahead and do one of these. Like occasionally they might be justified, but I would avoid them. Okay, so the final study I would want to talk about here, and this is generally clinical people won't do these types of studies, but occasionally they will. And what I'll do is I'll give you an example of particularly infectious disease studies which use ecological studies. So by ecological, I don't mean birds and trees and conservationism and that sort of thing. I mean the notion of ecological fallacy, which I'll talk about in a minute. So again, this is a primary database study, but typically the outcomes in these sorts of studies are aggregate counts or rates from different times. So for example, that might be a year, or spaces, which might be countries or localities. Often the data are routinely collected, so it might be hospital or government data, but the main point here is that our data are aggregates. So for example, I might notice in Townsville, there may have been 3 cases of dengue fever, and we do not have patient level data for Townsville. All we know is that Townsville had 3 cases and it's a hot tropical place. Okay, we don't know whether they were males, we don't know whether they were females, we don't know their ages. And we might have the data from 100 cities or 100 towns, okay? But it's aggregate data. They've already been summed up. We know the gender balance and the age distribution of these cities, but it is not linked to the individual patients. Okay. So as the outcomes are often counts or rates, we often use methods like Poisson regression or negative binomial regression in these types of studies. And probably a very common place they pop up is in vector-borne diseases. Okay, they're very, very common. So if we're talking about dengue, malaria, rotavirus, these are very, very common studies, study design. The major warning about these types of studies is our inability to get down to patient-level covariates, which might lead to ecological fallacy. So for example, we might find, and I'm just going to pick a silly example here, that Townsville has a higher prevalence of dengue than Brisbane. there's a higher proportion of males in Townsville than there are in Brisbane. So therefore basically males are at higher risk for dengue, okay? That would be based on ecological fallacy, because two things that might move together are not necessarily correlated with each other. Well, they might be correlated, but they're not directly correlated with each other, okay? It would be a spurious correlation. So we've got to be very, very careful with ecological studies that there's a good biological or clinical reason for our conclusions. Okay, so those were the study designs. There are some weird and wonderful variants among these study designs, but they're the main species, I guess you would say. So it is a major determinant. Study design is a major determinant on scientific quality. It can also have a major impact on analytical planning, so how we might analyse the data. And I just want to clarify these ingredients in analytical planning. So what is the likely nature of our outcome and predictors? What is the best way and practical issues for sampling? Can we use random sampling? Do we have to stratify? Is it a population-based study and we have to use convenience sampling? What are the likely sources of uncontrolled bias? Now, that's something we can't control through our design. That's what I mean by uncontrolled bias. Based on our study design, the study design we come up with, what statistical methods and modelling approaches should we use? And if it is meaningful, if it is a prospective study, it's experimental and so on, what sample size is appropriate? And I did talk about sample size last week. And remember, I just want to reiterate the point that not all that glitters is gold. There is more to Greek letters. There's more to good science than Greek letters. We've got to be very, very careful that sometimes we don't use these Greek letter formulas and just try and scam people into believing our research is an RCT, where it's not. It's clearly an observational study. We just got to be very, very careful there. Okay, so really from the methodologist's point of view, that study design plus analytical planning really is about the scientific quality. Now, there is something I'm leaving out there. It's also the problem formulation side and the dissemination, our ability to communicate it with people as well, that I'm not talking about. But from the methodologist's point of view, study design and analytical planning together result in good or bad scientific quality. Okay, so very, very briefly, I'm just going to talk about statistics and biostatistics. Statistics is the science and dark sciences, I don't know. The science and art of dealing with, so analysing and modelling, variation in data to obtain reliable results and conclusions. Biostatistics is the application of statistical methods to the health sciences. Biomedical sciences, public health, allied health, medicine, and so on. So biostatistics overlaps very much with the general discipline of statistics, but just note in biostatistics, there's a much stronger emphasis on particular methods. So for example, my bachelor's degree was in statistics. We did not do survival analysis in that subject. The survival analysis in the general discipline of statistics is extremely rare. In biostatistics, it's quite common. Okay, so it was only later that I came across those sorts of methods. So biostatistics in the public health and medical context is usually, but not always, the application of statistical models to community-based and clinical samples. And again, there's an emphasis on particular methods. Okay, so why do you have to learn biostatistics? The answer is you don't, okay? I think the main issue here is you need to know how it's used. It's useful to know what types of methods are used in what situations. So really, you've got a choice here. You can learn biostatistics yourself, or you can make sure that very early in the problem formulation part of a project that you include a biostatistician. Okay, it is useful to know some biostatistics. even if it's just the big picture side of it. In fact, I think the big picture side is much more important than the nitty-gritty from the researcher's point of view. So I would say that it's important for both conducting and disseminating health research because, again, understanding the methods allows us to communicate it because we've got a very good grasp of what we can and can't say. This is this strength of evidence things, okay? And I would just say, and by the way, I'm not going to say most grants, proposals, manuscripts, theses fail because of these, but a lot of them do, okay? That many, in fact, I wouldn't say most because I know scientific significance is a big part of why many grants fail, that the assessors just don't consider it important enough to be done. But you don't want to give people excuses, okay? So strong biostatistics, strong design, strong problem formulation, and so on are very, very important when it comes to your grant applications, your protocols, your theses, and so on, okay? Again, if you're talking to the right board of assessors here or the right ethics committee and so on, it's not hard for you to actually convince them how important your work is. Where the challenge for you is to actually convince them that your study has strong scientific quality. In other words, not only does the research need to be done because it's an important question, but it needs to be done because it actually could answer the questions. It doesn't matter how important something is. If your study can't answer the questions, it's not going to be accepted or funded or whatever. Okay, so the last thing I want to talk about, and I'm nearly there, and I did touch on this last week when it came to sample size, because it is very, very important. And that is how our study objective relates to our analytical approach, the statistical methods we use. Okay, and we need to acknowledge that there's a number of reasons why we might conduct research. And in my experience, a very large majority of studies fall into these three main categories. Predictive modelling, so performing analysis for predictive purposes, and this might include diagnostic testing or prognostic scoring models. The second is answering hypothesis testing, so answering a previously posed and very specific research questions. So this includes almost all clinical trials, okay? Anything involving an intervention and epidemiological studies with a particular study effect or a particular risk factor of interest. All other risk factors are really just nuisance variables from our scientific point of view that need to be adjusted for. We're not interested in them that much ourselves. It's a particular study effect that we're interested in. Now, I very much want to say that last part, that epidemiological studies with a single important risk factor and all of the other factors are nuisances. They need to be taken into account, but they're just a nuisance. That's in contrast to an exploratory study where it might also be epidemiological, but we've got a bunch of risk factors and none of them in our mind, are considered any more important than others. We're just trying to say, what are the important risk factors? We're not focusing on one, okay? So this type of study objective, has a very large effect on the design and the analytical approaches that we need to consider. So predictive modelling, the emphasis here, so remember diagnostic testing, prognostic scoring, risk scoring, the emphasis is on the individual patient. We want a diagnostic test result or a prognostic score or so on for individual patients. That's ultimately what we want out of this type of study. Okay, and diagnostic tests and prognostic models, so for example, survival analyses and so on, they're very common types of predictive modelling studies. Predictive studies rely on a very strong relationship between our outcome and predictors. Okay, so for example, if we're talking about a standard continuous outcome, we would want a very strong R-squared, above 90% in a predictive modelling. Okay, so for example, BMI is a risk factor for type 2 diabetes. Okay, it is a risk factor for type 2 diabetes, but we would never use BMI alone as a prognostic indicator. We're not going to use BMI as a prognostic test because there are a lot of overweight and obese people who do not have diabetes, but we do know that high BMI is a risk factor for diabetes. Okay, so that's the difference there, that we need a very strong relationship in predictive modelling. Okay, if it's something like a diagnostic test evaluation, you've got it or you don't. We wouldn't use R-squared because we've got a binary outcome. We would use something like diagnostic accuracy. So that might be specificity, sensitivity, area under the ROC curve, those sorts of things. Okay, so the take-home message here for predictive modelling is fit to the data. In other words, how well our model fits the data is much, much more important than statistical significance. All statistical significance tells us is that we could use this test, this method, this model on a similar population. It doesn't tell us that it's a good model, okay? By the way, lack of statistical significance is important because it means the model can't really be generalised to anybody else. But a p being less than 0.05 is not something that is important by itself in predictive modelling. We need the fit to the data, so the R-squared, the diagnostic accuracy, those types of things. Okay? Hypothesis testing, okay? And this is why I did mention these last week. They are studies that consider a specific research typically to address a single primary hypothesis. And I should say that's the primary hypothesis. We can have secondary ones. As such, and if it's sensible, they should be prospectively and formally powered, okay? So an RCT is the perfect example of a hypothesis testing study, and we should use our Greek letter formulas for these types of studies, okay? So again, the most common examples are randomized controlled trials, and I should really say trials of any description, and population studies considering a particular and well understood risk factor. In other words, the literature very strongly justifies our identification of a risk factor, and all of the other risk factors aren't that much of interest to us. So we have a single X variable of interest. All of the other X variables are nuisances. In these studies, we typically have this single predictor, I just said that, of interest, but they can have other covariates too. Okay, finally, we come to exploratory studies. These are the what are studies. What are the prognostic indicators? What are the risk factors for diabetes, for example? Here, we don't necessarily have a very strong scientific understanding of the relationships between the outcome and all of the predictors, whether they be risk factors, confounders, effect modifiers, and so on. And we want to get a better idea about it. That's the point of the study. So for this reason, these studies typically involve a large number of predictors, which may or may not represent potential risk factors, confounders, or effect modifiers. We don't really know. This is a let's see what happens type of study. And I don't mean that in terms of poor strength of evidence. It's just we know which are likely to be risk factors, but we want to quantify them. We want to say, yes, they are, no, they're not, and so on. In these types of studies, because it's a complicated relationship between bunches of variables, we have limited knowledge, and we should really avoid formal sample size calculations. If we do use them, we're pretending we know stuff that we don't, okay? And they can actually be misleading. So often people will talk about the rules of thumb or the informal approaches. If, for example, we have a continuous outcome, a common rule that is used to, I shouldn't say power a study because it suggests that we are doing it in a formal way, but a common method for the sample size calculation is to have 60 plus 5 additional people for every predictor we have, okay? If it's for a logistic regression or a survival analysis, we often use the 10 EPV rule. Now, see last week's lecture notes on how to do that. Another possible approach, and I did mention this last week, and this is very, very involved to do this. So again, you can do it if you've got a biostatistician who has too much time on their hands. You can use simulation methods to sort of get a educated guess as to what the sample size might be. But this is particularly labour-intensive type of work. But if you're talking about an NH and MRC grant, it might get you over the line with it. Okay, so I just want to finish off with a statement, and that is try and get us involved early in the process, okay? Because to call the statistician after the experiment is done may be no more than asking him to perform a post-mortem examination. He may be able to say what the experiment died of. And I want to apologise for the gender-specific language there, but Ronald A. Fisher was like World War II vintage. And women didn't exist in World War II, apparently. They just weren't around. Okay, so everything was he and him then. Okay, thank you. Any questions? Nope. Okay, none at all. Come on, there must be some. Yep.
So if you were looking at prevalence of an infection, for example, in a systematic review, would you exclude case control studies because they don't show?
Well, that's exactly right, because the prevalence in a case control study is very artificial. Okay? In fact, I can almost guarantee it's going to be 50%. It's going to be 25%. What would be 1 to 3? That would be the 25%. Sorry, it might be 50%, 33%, 25%, or 20%. Because people do 1 to 1, 1 to 2, 1 to 3, and 1 to 4 case control studies, and that's about all. Okay? So very much so. A case control study is not a cross-section of the population. It's artificial. Okay? Yeah. By the way, just watch out that I'm talking about if the case and control status was based on the outcome you're considering, okay? I probably wouldn't use them across the board. Sorry, I should reiterate the question. The question was, if you're doing a systematic review and some of those studies are case control studies, should you avoid using your estimate of cases over everybody as a measure of prevalence? And my answer is yes, because that is very much an artificial estimate. It's an artifact of the study design. It's got nothing to do with being a cross-section of the population. Okay? Yeah. Okay. Thank you very much. Okay. I didn't turn that off.